So imagine you're working on your computer, right? But your machine has absolutely no hard drive, only RAM.
Which is a pretty terrifying thought for any workflow.
Right, it's a nightmare. Every single high-resolution image you open, every document you read, it all has to stay open on your desktop, like permanently.
Right, because there's nowhere to store it.
Exactly.
Yep.
So by the 15th image, your system is lagging.
Yeah.
By the 20th, your screen is just, this mosaic of frozen pixels, and the whole operating system basically crashes because there's zero computational memory left to actually run any applications.
Yeah, and that is actually the exact architectural nightmare happening inside the brain of modern generative AI right now, especially when you try to have a really long, image-heavy conversation with it.
It completely crumbles.
It does. It just crumbles under the weight of its own short-term memory.
And it's what researchers are calling a visual token explosion, which sounds dramatic. But it's the primary reason your favorite AI assistant gets a severe case of goldfish memory the second you start iterating on complex visual projects.
Yeah, anyone who uses these tools knows that frustration.
Oh, totally. If you've ever felt the sheer frustration of an AI just hallucinating past a certain point in a design workflow, this deep dive is specifically for you. We're unpacking a state-of-the-art research paper from Peking University in Tencent, and it's called Cognitive Structured Multimodal Agent for Multimodal Understanding, Generation, and Editing.
It's a mouthful, but the implications are huge.
Huge.
Sure.
Our mission today is to really figure out how they solved this memory bottleneck and, what it actually means for the future of your daily workflows.
To really appreciate the solution here, we kind of have to isolate the flaw in the current industry standard, right? Because right now, the default approach in AI is the unified or monolithic model.
Right.
And a prime example evaluated in this paper is a model called Bagel.
Okay, so when you say Bagel is a monolithic model, I'm picturing like a single massive neural network trying to play every single instrument in the orchestra at once. Like it's processing your text prompt, analyzing uploaded images, generating new pixels, and trying to track the entire conversation history without any specialized departments.
That is actually a really highly accurate visualization. And the mechanism it uses to recall information from that shared history, that giant orchestra, is called implicit attention.
Okay, let's unpack implicit attention, because to me, that sounds like what happens when I'm vaguely listening to a podcast while I'm cooking. Like, I hear the words, but I'm not really processing the meaning. Why does that mechanism fail so badly here?
Well, mathematically speaking, the AI's computational focus is a zero-sum game.
Okay.
If the model has, say, 100 tokens of data in its active context window, it can allocate a solid percentage of its attention to each one, right? It can reason effectively.
Sure.
But an image isn't just one token. A single image can be composed of hundreds or even thousands of tokens.
Oh, wow. Because visual data is so computationally expensive.
Exactly. Extremely expensive. So if we are on, turn 15 of a project and we've gone back and forth generating 10 different images.
That's tens of thousands of visual tokens.
Right. They're just sitting there in the active context window, actively diluting the attention pool.
Oh, man. So the math just becomes brutal.
It really does. When you flood the context window with that many tokens, the attention allocated to any single crucial detail from, turn 2 drops to a fraction of a percent.
It just disappears.
Older details literally fade into statistical noise. The model just doesn't have the computational budget to reason anymore.
So it suffers from semantic drift.
Right, semantic drift, it starts blending images together or hallucinating entirely because it's just overwhelmed.
Give me the damage report on this. Like, how bad does it actually get in practice when the model drops those frames?
It's pretty staggering, honestly. The researchers tested Bagel on complex multi-turn tasks, and on the hardest visual context retrieval challenges in their benchmark, Bagel retrieved the correct historical image less than 3% of the time.
Wait, really? Less than 3%?
Less than 3%.
You couldn't even use that for a middle school art project, let alone rely on it for professional workflow.
Yeah.
But looking at the industry right now, the default solution to this seems to be, brute force scaling. Like, just build a bigger context window, give the computer more RAM, throw a massive 32 billion parameter model at the problem.
Which is what a lot of companies are doing. But this paper definitively proves that that is a dead end for sustained multimodal interaction.
Interesting. Why is that?
Because scaling up the parameters just delays the inevitable token explosion. You aren't fixing the fundamental mathematical flaw of implicit attention dilution.
Right.
You're just making a slightly larger bucket that still has a massive hole in it.
Okay, so if a single massive neural net is the wrong approach, we clearly need a paradigm shift. And what these researchers built, the Cognitive Structured Multimodal Agent, or CMA, it moves away from that monolithic brain entirely.
Completely, entirely.
They essentially built a highly organized corporate department, right?
Yeah.
4 distinct, specialized modules handling the workload.
Yeah, they completely externalize the memory. So the AI no longer has to hold every heavy image in its active context window all at once.
Let's map out this department because the architecture here is genuinely fascinating. We start with the Perceptual Abstraction Engine, the PAE.
Right.
If we stick to our corporate metaphor, this is our archivist.
Yeah.
But I'm assuming it's not just like saving raw JPEGs to a desktop folder somewhere.
Far from it. The PAE is a really sophisticated vision language encoder. Whenever an image enters the chat, the PAE compresses it into a highly structured memory entry.
Okay.
So it generates a lightweight visual thumbnail, applies specific semantic attribute tags, and it writes a really detailed natural language description of the scene.
Oh, got it. So it's translating all that heavy pixel data into lightweight, searchable metadata.
Exactly.
And once the archivist does that, it hands the file off to the second module, right? The Episodic Visual Memory, or EVM, basically the filing cabinet. And to be clear on the technical reality here, if we're talking about modern AI, this filing cabinet has to be a vector database, right?
It is indeed a vector database, yeah. It stores the visual thumbnail and those semantic descriptions as mathematical vector embeddings.
Which is a super crucial distinction for anyone listening who builds these workflows. Because storing it as a vector means the AI can perform semantic search.
Right. It's not just a keyword lookup.
Right. It's not looking for an exact file name like imageera1.jpg. It's mapping the meaning of the image in mathematical space. So all those heavy visual tokens are officially out of the active context window. They're filed away.
Safe and sound. And they're occupying zero space in the ongoing dialogue, which immediately stops the token explosion.
Incredible. But a vector database is completely useless if no one knows how to query it properly. Which brings us to the third module, the Cognitive Retrieval Engine, or CORE.
The librarian.
Librarian. What exactly is their job?
The librarian's role is to perform cross-modal reasoning. So when you prompt the AI, the core analyzes the current state of your dialogue, calculates what you're asking for, and queries that EVM to fetch only the highly relevant historical images.
Okay, and once the librarian fetches that specific file, it hands it to the boss. The fourth module, the Multimodal Executive Controller, or MEC.
Exactly. And the MEC is what integrates your new prompt with that one specific retrieved memory and infers your intent, like, do you want to generate something new, edit this old image, or just chat about the context?
Right.
And then it plans and executes the final action.
I want to pressure test this architecture a bit. Let's look at a scenario where a standard monolithic AI would just completely lose its mind, and let's see how the CMA handles it. There's a 20-turn dialogue in the paper that really highlights the difference here.
Oh, the biological cell experiment. Yeah, it's a perfect stress test for this.
Right. So the user asks the AI to generate a microscopic view of healthy biological cells with a bright green fluorescent stain. The AI generates it beautifully. The archivist encodes it. The filing cabinet stores it.
Smooth so far.
Smooth so far. But then the user pivots completely. Over the next, 15 turns, they ask the AI to generate a stargazing dome, a clean room with robotic arms, a communications satellite. The context window is now just flooded with space and manufacturing jargon.
And crucially, it's flooded with the heavy visual tokens of all those new scenes.
Right. So then on turn 18, the user says, modify this microscopic view to show infected cells. Keep the exact same arrangement, but change the fluorescent stain to a deep red color.
Right, which is a massive jump.
Huge jump. A unified model like Bagel is going to try applying its implicit attention across the satellite, the clean room, the telescope, and the cells simultaneously. It'll probably give you, a red clean room.
Yeah, exactly. But the CMA bypasses all of that semantic noise. The MEC, the boss, recognizes the command as an edit. The librarian, the core, searches the EVM vector database.
Oh, yeah.
And it completely ignores the space and factory embeddings because their mathematical distance from microscopic view is just too far.
It just screens them out.
Exactly. It retrieves the exact thumbnail of the green cells, and the MEC uses only that isolated baseline image to apply the red edit.
And they push it even further. Like turn 20, the very end of the session, the user says, remember the initial microscopic view of the healthy cells with the bright green stain? Change that stain from green to a vivid purple.
It's such a hard test.
It has to ignore the red infected cells it just made, reach all the way back to the start, and it nails it. Zero hallucination.
That is the power of decoupled memory right there. You eliminate the semantic drift entirely.
Here is my glaring issue with this whole setup, though. Like, you can build the most elegant librarian and archivist modules in the world, but they still have to be trained to communicate with each other.
Yeah.
And I followed the data space pretty closely. I don't know of any massive open source data sets that have 20-turn, highly specific visual callbacks annotated for training long horizon retrieval.
You're completely right. You've spotted the exact hurdle the researchers faced. The data simply didn't exist.
Okay, so what did they do?
Well, most multimodal data sets are single turn, like what is in this picture, or maybe 2 turns at best. They completely lack the fine-grained turn-by-turn annotations you need to teach an AI which specific historical image to recall during a long, meandering project.
So if the data doesn't exist, you basically have to synthesize it. Did they just use another large language model to brute force a data set?
Pretty much. They built what they call a unified scenario engine. They utilized Gemini to act as a user simulator and programmatically generated hundreds of complex 20-turn conversations.
Wow.
But the really vital part is that the engine automatically generated the ground truth retrieval annotations for every single turn. So it created this massive virtual obstacle course for the AI.
But wait, if you're just using Gemini to auto-generate an obstacle course, how do you prevent the AI from learning lazy shortcuts? Like, if every question is really obvious, the librarian isn't actually learning semantic retrieval, right? It's just doing basic keyword matching.
This is where their evaluation benchmark, the M2CA bench, introduces a genuinely brilliant concept. They use what are called hard negatives.
I was looking at that in the methodology. A hard negative isn't just a wrong answer, right? It's an active decoy.
Exactly.
It's a high similarity confounder designed to test if the AI is actually paying attention to the specific pixels or if it's just skimming.
How tricky these decoys really are.
Let's do it.
So the user generates an image of a modern car manufacturing line. Robotic arms assembling silver cars, bright factory lights, and notably, bright welding sparks flying everywhere.
Got it.
Then the user asks for a variation. The exact same factory, but pause for the night. So the AI makes a second image. Same cars, same robots, but the lighting is dim blue, and crucially, there are absolutely no welding sparks.
Okay, so 2 very similar images.
Right. Then fast forward to later in the conversation, the user asks, compare the active factory image with the pause night version. What are the main differences in lighting?
A lazy AI just reads day and night in the text prompt and spits out a generic answer about the sun. Or it just grabs the first factory picture it finds and guesses.
Exactly. But to get the reward signal during training, the librarian has to retrieve both near-identical factory images from the vector database, distinguishing them from any other industrial images.
Wow.
Then the MEC has to analyze the specific pixels of both. The correct answer must mention the cool white versus dim blue color temperature, but it must explicitly mention the absence of the warm-colored welding sparks in the night version.
That is so specific. It forces the AI to prove it is performing true visual reasoning.
Yeah, it really does.
But how do you mechanically train that behavior across decoupled modules? Like, the paper mentions supervised fine-tuning and reinforcement learning, but how does the reward actually travel through this system? If the librarian finds the right file, how does the archivist know it did a good job summarizing it?
It's all about the backpropagation of the reward signal.
Okay, break that down for me.
So in the reinforcement learning pipeline, if the final answer is correct, the system sends a positive reward back through the entire chain. The core librarian gets rewarded for its search query, and that signal travels all the way back to the PAE archivist.
So the archivist effectively learns, when I included the phrase bright welding sparks in the metadata, it led to a successful retrieval by the librarian later. I should prioritize that level of fine-grained detail.
Exactly. It's optimizing its own internal communication language. The archivist learns to write better summaries specifically so the librarian can find them more easily in the future. It is just an incredibly elegant feedback loop.
Let's talk real-world performance, though. Because on paper, breaking this into 4 separate modules communicating with each other, it sounds computationally heavy.
It does sound like it.
Did they just trade a memory bottleneck for a processing bottleneck? I mean, adding all these steps, encoding, vectorizing, querying, executing, it seems like it would slow the inference time to a crawl compared to just dumping everything into one big monolithic context window.
You'd think so, but the metrics here totally upend that assumption. Let's actually compare their new 8 billion parameter CMA model against that massive 32 billion parameter monolithic baseline we discussed earlier.
So a model a quarter of the size.
Right, a quarter of the size. Over a full 20-turn session, the 8B CMA achieved a 91.4% retrieval accuracy on the MTCA bench.
Wait, the 32B bagel model was hitting less than 3% on the hardest tasks. The CMA is hitting over 90%.
Over 90%. And overall, the CMA beat the 32B model by a margin of 8.2% across the board.
It's wild.
But to address your processing bottleneck question, because the CMA completely bypasses the visual token explosion, it is actually significantly faster.
Right.
By only looking at the specific, relevant images handed to it by the librarian, the per-turn inference time dropped from 23.1 seconds in the monolithic baseline down to just 12.7 seconds.
It cut the processing time almost in half. So the system is doing more mechanical steps, but because the computational payload it's carrying at any given moment is so much lighter, it just sprints past the bigger model.
Exactly.
It basically proves that for complex workflows, highly structured, specialized memory fundamentally beats brute force parameter scaling.
And the really exciting part is the team didn't just leave this as an academic lab experiment. They translated this architecture into a deployable, real-world framework called the CMA harness.
Now, the CMA harness is where this moves from an abstract paper to a tool I want on my desktop tomorrow. They expanded the MEC, the boss module, by giving it a registry of 17 different callable tools.
Yeah, so the agent can now autonomously decide to run a web search to fact-check a prompt, fetch a specific image from a URL, run a background removal tool, overlay text, or even compose multiple images together into a single layout.
But the killer feature here is what happens to that EVM filing cabinet. Because in a typical chat session today, when you close the browser tab, the AI's memory is just wiped.
Gone forever.
Right.
Yeah.
With the CMA harness, the vector database becomes a multi-session persistent memory.
This is huge. It organizes the memory into user-level scopes, so it actually remembers your durable preferences, project facts, and specific reusable visual assets across completely different sessions.
So, okay, if you are designing a marketing campaign on a Tuesday, and you spend an hour generating the perfect company logo and, product shots, you log out on Friday, you log back in, open a new session, and just say, take that logo we finalized on Tuesday and put it on a billboard.
Yep.
The archivist and librarian query the persistent database, fetch the exact pixel-perfect embedding from Tuesday, and apply it. No token explosion, no hallucination, no starting over from scratch.
It remembers your specific project context across days, weeks, or theoretically even months. It shifts the entire paradigm from interacting with a transient amnesiac chatbot to collaborating with a persistent, long-term creative partner.
It's a massive leap forward. We've gone from monolithic AI models that just drown in their own visual data, paralyzing your workflow, to a sleek, modular system that files, retrieves, and acts on visual memories, just like a highly organized human team. Faster inference, 90+% accuracy, and persistent memory.
The architectural efficiency here truly proves that how an AI organizes information is just as critical, if not more so, than how much raw compute power it has.
Absolutely. Well, I want to leave you with a final thought to pull on as we wrap up today. If an AI can now maintain perfect visual consistency and persistent memory across days, weeks, or months of interaction, what happens to the creative process itself?
That's a fascinating question.
Right. When your AI collaborator remembers the exact mathematical shade of red in a sunset from a project you worked on 3 months ago, and honestly remembers it better than you do, does the boundary between human imagination and machine memory begin to blur?
When the machine becomes the ultimate, infallible keeper of a project's continuity, it definitely changes the dynamic of who is actually anchoring the creative vision.
Are we outsourcing not just the rendering of our ideas, but the actual continuity of our own creativity? Definitely something to chew on the next time you find yourself wishing your AI could just remember what you talked about yesterday. Fortunately, it looks like that day has finally arrived. Thanks for joining us on this deep dive into the bleeding edge of generative AI. We will catch you on the next one.